Let's talk about socks. So I do my laundry, and I'd clean out the lint trap in the dryer, and I'd see all this lint that was there. And it made me think, how much of my clothes am I losing each time I'm doing my laundry? So that's what this experiment was all about. Except rather than focus on all my clothes, I thought, let's just focus on socks. Something easy, something small that I can weigh. So I had done this experiment before in part 1, check the description, but I didn't really account for humidity in the environment and its impact on the final weight. It turns out it's quite substantial. So when I was measuring these socks, I didn't realize that a lot of that percentage weight was actually the humidity. What we did in part 1 is we weighed, washed, dried, and then weighed. And we're going to do the same thing here in part 2, except we're going to take one data point at room conditions, and then we're going to take a second data point using the desiccant container. And we're going to leave the socks in there for a while to remove as much moisture as we can, and then we'll do some analysis on it. Let this video finish playing. All right, so we collected the data and we're going to analyze it two ways. This is the first way. So we have the different sock and we put a pin on each one for identifying. So we'll use the colors as the identifier. We have the different laundry cycles, the percent relative humidity average, and then we have the wet sock weights. So then using laundry cycle 0, 1, and 2, we graph it and we use extrapolation to get to the 0% humidity point. And we make the assumption that at the 0% relative humidity point that all of the moisture will be pulled out of the sock. And so we'll be left with a dry sock only. All the extrapolated y-intercept points here at the 0% relative humidity are shown in this table. So we carry them forward here and then we calculate the delta. So the negative 0.13 is the difference between this number, and the 0.16 is the difference between this number and that number. We get an average delta for that sock. Then we do the same thing but on a percentage basis. So negative 0.394% is negative 0.13 divided by where we started, 33.68, and that's how you get those percentages. So we'll use column 1 for a linear extrapolation, and then in part 2 here, columns 2, we're going to do an exponential extrapolation. So first off, we do the linear extrapolation, which has a constant weight loss. And when we do that, our average loss is 0.12 grams per laundry cycle. And if you carry that all the way to the x-intercept with no sock weight remaining, it's about 300 laundry cycles. And then when we do our exponential decay, which means that each time you wash a sock, we're going to lose the same percentage, so it slows over time. And because mathematically I'll never reach 0, I put 20% here, material remaining, and we'll call that dissolved. So then you get some values where the average we'll say is about 460 laundry cycles. So let's graph that so it's a little clearer. If we use the averages on a weight basis, you have this right side axis. But if we convert that to a percentage basis, so it can be any weight of sock that we start with, you can find that on the left side here. If you look at it from like a linear perspective, it doesn't make the most sense, because if we took a sock and we cut it in half, so we're left with half a sock, mathematically this linear extrapolation assumes that that half a sock would be losing the same mass per laundry cycle as that full sock. Meanwhile, if we do the extrapolation with the exponential, you can see it gets really slow after this elbow and will take forever. It will never fully come to 0 no matter how many laundry cycles you put the sock through. So it's slowing over time. However, in reality, there's the case that as the sock loses more of its mass, it might actually gain more surface area, and so that would cause it to lose more mass on the next laundry cycle, etc., etc. And then at some point, all of it might just fall apart and get caught in the lint trap. So I just threw a ballpark number here of 20 to 30% for this whole dissolving phenomenon. You can pick out your favorite number on this graph and do it your own way, but I just chose that. So how do we do that? So if we say 30% is dissolved, I have it align here to the linear extrapolation, goes down to 200 laundry cycles. And then you can do the same thing with the exponential and draw the line down, but I said, no, let's just give a little extra to give it a full range possibility, and so I took it down to the 20% line, and so then that's about 460. So let's analyze it with a second method. Here we're going to use the moisture isotherms charts that are found in literature. So if you look at this moisture regain chart for desorption of moisture from cotton, specifically soda boiled cotton at 25 degrees Celsius, you'll see that in the region that we collected the data points from about 50 to 14, it's not exactly linear to get all the way to 0. In fact, I kind of drew this red dotted line here as my estimate of what the linear would be. As you can see, it doesn't cut out all of the moisture. We should be getting a value that's lower. So let's go back to our data and use this chart instead. Some of the assumptions of using this moisture retain isotherm chart is that chart is for 100% cotton. Here we're using a sock that is not 100% cotton. It's only 39% cotton. And so none of the other components of the sock are going to influence how much moisture is left. And also the cotton that's found in the sock will have the same desorption as the soda boiled cotton. If you look at these charts, the absorption and desorption curves are different. However, these socks started from a fully saturated wet environment, the laundry, and then we are taking it from there down to 0. So we should be on the desorption curve. So let's do the calculations. So the original chart from literature is given as a moisture regain chart, but we don't know the weight of the dry material, nor do we know how much water is in these socks. So instead, we convert it over to a equilibrium moisture content chart. There we have the weight of the water on the top, which is unknown, but we have the weight of the dry material plus the weight of the water that we do have. That is our wet sock. So I've graphed them both on the chart here, and now let's do the calculation to find out our dry sock. Okay, so we take the humidity, we find that on the chart. We have our wet sock weight. We say that only the cotton is absorbing the moisture in these socks. So here's the 39% of that weight for the cotton only. Then we find for this humidity what the equilibrium moisture content is. So I've done that, so 5.89%. And then we multiply 5.89% times the cotton only weight. That gives us the weight of water only. And then we subtract this water only weight from the wet sock. So that will give us the weight of the dry sock only. And then I've averaged for the two data points, one at the high relative humidity percentage and one at the low relative humidity percentage. This follows for what we did in analysis part 1, just now with this new set of data. You'll notice that in part 1, this was about negative 0.12 average, and in this analysis, it is about 0.10. So it's a little bit slower of a decrease. So because it's a slower decrease, it takes more laundry cycles to get to the same amount of decay. So in our previous part 1 of our sock weighing, we saw that most of the loss of the sock from laundering came from the drying process because the rock's tumbling, it's at an elevated heat, so it's kind of like a rock tumbler. It's just abrasion after abrasion continuously. And we measured the drying cycle was about an hour, 9 minutes, and 16 seconds, and I made sure that that was the exact same for laundry cycle 1 and laundry cycle 2. So we can convert our estimates for the number of laundry cycles into a time duration, a continuous running dryer. How long would it take until these socks fall apart, dissolve, disappear, and lower bound of about 10 to 22 days, 12 to 26 days continuously. So let's say about a month, you would have no sock remaining. I performed this experiment for 2 laundry cycles, primarily because each time I performed a desiccating step, it took an extremely long time for the moisture to go from about 50% relative humidity, and the lowest I got it was about 14% relative humidity. And since that took such a long time to do it with a desiccant, we definitely could do more iterations if we had a faster desiccating process, and that would allow us to do trending further out faster. And that would let us find out what really happens when we get to these large number of laundry cycles. Is it going to decay faster or is it going to decay slower? Which one is it? We don't really know at this point. These moisture data points that we collected at room temperature, unlike the situation where I put the socks in a box for the desiccant, the room temperature and the room humidity wasn't controlled as much. So when we collected a data point there, it was just whatever the probe said at that point. We don't know definitively the equilibrium condition that the sock was experiencing. How that could be improved is using an environment with a known relative humidity, known temperature, and holding the socks there instead for that second data point. When I talk to people, a lot of their feedback is they want to know about the sock where when you walk around with a sock, more of an abrasion type experiment from a shoe. And so there are standards out there, Martindale testing for abrasive against fabrics and other counts like that. I'm not too familiar, but maybe someone could do one of those and compare that against what we saw from this laundering experiment and how much mass loss we got from that. And that's it.